and welcome. My name is Joanna Perez, Digital Marketing Specialist for IEEE. IEEE is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. Before we begin, please note a few housekeeping items. At the bottom of your screen are engagement tools that you can use. All tools are resizable and movable, so feel free to move them around to make the most out of your space. Please note that we recommend using a wired internet connection to access today's presentation and closing any background programs that can cause issues. There is no dial-in number for this event, so please make sure your computer speakers and headset are turned on and the volume is up so that you can hear our presenters. If you have questions about today's presentation, you can submit them through the Q&A widget on your screen or click the purple Q&A icon at the bottom of your screen. We will answer as many questions as time allows. Finally, the on-demand link for today will be emailed to all registrants approximately 2 hours after today's session. Our virtual event today is the Internet of Things, use cases, applications, and key elements. If you would like to tweet about this event, please use the hashtag #education@IEEE. At this time, I'd like to hand it over to Sasky.
Thank you very much, Johanna. It is my pleasure today to welcome you all to the IEEE Academy's webinar. And the title of today's presentation is the Internet of Things, Use Cases, Applications, and Key Elements. It's going to be given by Professor Xiang Sun, who is currently, just a brief biography, he's currently an assistant professor with the Department of Electrical and Computer Engineering at the University of New Mexico. And he received his PhD in electrical engineering from New Jersey Institute of Technology back in 2018. And his master's and bachelor's of engineering from Hebei University of Engineering in 2011 and 2008, respectively. And he has a diverse set of research interests. This includes free space optics, wireless networks, cooperative machine learning, Internet of Things, edge computing, green communications, as well as computing. And he's received a number of different prizes and honors and awards over the years for his research. This includes the New Jersey Institute of Technology Ross Fellowship in 2014 to 15. He got a Best Paper Award in ICC in 2016. In 2017, he was an IEEE Communications Letters Exemplary Reviewers Award. In 2018, the NJIT Hashimoto Prize. In 2019, the IEEE Communication Society Best Tutorial Paper Award. He's currently an associate editor for the IEEE Open Journal of the Computer Society and Digital Communication and Networks. So it is my pleasure to welcome Xiang, and the floor is yours, Xiang. Thank you very much.
Thank you, Sassy, for being the moderator for my talk, and thank you so much for the great introduction. And thank you all for having me here. My name is Xiang Sun. I'm an assistant professor in the Department of Electrical and Computer Engineering at the University of New Mexico. So today I'm going to give you a very brief introduction of the Internet of Things, explaining some use cases, applications, and the key elements in the context of IoT. So before I start my talk, I would like to acknowledge Dr. Paul Chang and Dr. Kim Wang Raymond Cho. Both of them are the technical editors of the IEEE Academies on Internet of Things. So some of the slides in my talk are from their lecture slides for the IEEE Academies on Internet of Things. So this is the outline of my talk. First of all, I would provide the concept of the Internet of Things, explaining what is IoT system and IoT devices. Then I will give you some applications about for the IoT to explain how does the IoT facilitates our daily lives. Then I will introduce the IoT communications, which is one of the key elements in IoT to connect different devices together, and also provide some features about the IoT communications, why the IoT communication is so unique. Then afterwards, I will explain how to apply the artificial intelligence and the machine learning models to analyze the data that are generated by different devices to extract the high-level knowledge and the models. So finally, I will discuss some challenges of the IoT and some potential solutions. So the Internet of Things is it's kind of like an architecture where the different smart devices and interconnect through these data networks to interact, collaborate, and learn from each other without human interaction. So here the smart devices are referred to as IoT devices, and those IoT devices have different functions. For example, IoT device could be an actuator, could be a sensor, a drone, a computer, or even a server. But all of the IoT devices should be equipped with the communication modules to achieve the data exchange, to achieve the communications. So here the data networks in the IoT architecture plays a very, very important role to enable different IoT devices interact with each other. And there are different types of the data networks in IoT, such as the wired or wireless networks, the local or wide area networks, and so on. So one question you may ask is, what are the IoT devices, or how do we categorize them? And there are many definitions of the IoT devices and ways to categorize such devices. So broadly speaking, IoT device can be categorized into the consumer IoT, such as the Amazon Echo Ring cameras, your smart TVs, your smart refrigerators, and also the medical IoT, which is also called the Internet of Medical Things, such as the wireless pacemakers, the industrial IoT, such as the IoT robotics, like 3D printers, and the vehicle IoT, which, for example, the autonomous and the unmanned vehicles, the battlefield and the military IoT, which is also called the Internet of Battlefield or the Internet of Military Things, and so on. So here, different categories can be further divided into different classes. For example, the medical IoT here can be further categorized into like wearable devices, such as wearable patch used in the motion sensors, and the vital sign monitoring that it can be used for the precision medicine. So the categories of IoT devices are not unique. Here's another way that to categorize IoT devices. The device around us, like most of our consumer IoT and the autonomous or unmanned vehicles, devices in us, like the embedded device, and the devices on us, like our smartwatch, the wearable device, and the mobile devices. So these slides just show one example of wearable physiological sensor network, which combines the smartphones with body sensors that are on us. The smartphone serves as a base station or a gateway with a built-in Bluetooth or Wi-Fi module. So the body sensors can sense information such as the temperature, the heartbeat rate, the ECG, and the blood pressure. And then those sensed data can be transmitted to the smartphone through Wi-Fi network or the Bluetooth link, which those sensor data are going to be displayed, received and displayed through the app in our smartphone. So there are different types of the IoT devices that have already been deployed in the world. But how many IoT devices will be there in the world? And will different companies apply the IoT technologies to benefit their business? The fact is that the number of the IoT devices in the world is growing exponentially. So this figure shows that the number of the active IoT connections over the year. So despite the chip shortage and the COVID-19 extended impact on the supply chain, the global number of connected IoT devices is expected to grow 9% Probably you cannot see these numbers very clearly, but the growing is around 9% from 2020 to 2021. Also, by 2025, there could likely be more than 27 billion IoT connections. Also, the companies in the world are increasing their IoT spendings to facilitate their business, and finally increasing their revenues. So these figures shows that the global spendings on the enterprise IoT technology. The amount of the spending is expected to grow 24% from 2020 to 2021. And by 2025, the overall spending is projected to around $412 billion. So what is the fundamental transformation that IoT device and IoT technology bring? If you heard the word cyberization, this is what IoT brings us. So cyberization is a process of forming a new cyber world, which transform our current, not only physical, social, but also mental worlds into normal cyber combination worlds by using the IoT devices and the related technologies. So the cyberization basically facilitates us better and more efficiently, and let us more efficiently understand our physical, social, and mental worlds. So next, I'm gonna give you some applications to further explain how does IoT facilitate our lives. So the first application is I want to talk about is smart groceries delivery. So imagine that if you have the smart refrigerator in your home, and this smart refrigerator is able to detect the products that in the refrigerator based on, for example, the RFID tags of the products, which means that the smart refrigerator is able to communicate with those tags, which contains the information of the products, such as product name, the quantity, the expiration date, and so on. Also, the smart refrigerator is able to learn families' dietary habits and the allergies from the prescriptions. So if a product that is required by the family is in short supply, then the smart refrigerator can find a grocery store that, for example, offers the lowest price for that product, and then automatically place an order to the grocery store. Meanwhile, the smart refrigerator can automatically send the order and check the order information to the user's smartphone, and the user can cancel or check the order anytime. So on the other hand, the grocery store can need to send their products information, such as the price and the products the quality. For example, it's, the products is organic or not organic to the smart refrigerator. So the refrigerator would select the best grocery store that fits for the family's dietary habits and the preference. Also, the selected grocery store need to process the received orders and deliver the orders to the family in time. So in this smart groceries delivery process, this smart refrigerator plays a very important role to interact with the RFID tags of the products, the grocery stores, and the users, and also finally make the intelligent decisions such that the user can automatically receive their required products. So the next application I want to talk about is probably you are very familiar with is a smart home. So assume that you have purchased many smart devices like smart light bulbs, smart door locks, smart media player, and thermostat. So and then you deploy these devices in your home. So all those devices are connected to the Wi-Fi access point. Also, the Wi-Fi access point can check the user's calendar to know your schedule, and can learn your preference based on the historical behavior data, such as what is your preferred room temperature and humidity in different seasons. What are your favorite songs and movies in different time period? So if the Wi-Fi access point find a meeting in your calendar tomorrow, for example, and it will determine the best time to wake you up based on the upcoming road conditions and the distance to the destination. So also it will control the thermostat to adjust the room temperature according to your preference. Also it will turn the light on and play your favorite songs to wake you up. So the last application that I would like to mention is mixed reality or hybrid reality. So what is a mixed reality? Mixed reality is a user environment where digital data and the physical reality are well aligned to facilitate the interactions among the real world and the digital objects. So there are two important technologies in mixed reality: IoT and augmented reality. So basically in the mixed reality, users are wearing these AR glasses or augmented reality glasses or the smart glasses. And so once a user is capturing the IoT device through its the AR glass, the related information of the device will be transmitted to and displayed at the AR glasses. So for example, if the user is looking at the smartwatch here, and then the recent short message will be transmitted from the smartwatch to the AR glasses and displayed at the AR glasses. If the user is looking at the air conditioner, then the temperature and the humidity values, which are captured by the sensors in the air conditioner, will be transmitted to and displayed at the air glasses through the D2D communications. So also if the user is looking at those the machines or the 3D printers in a manufacturing company, then the status of the machine, such as the temperature, the noise level, the inspection time, all those information will be transmitted to and displayed at the AR glasses, right? So now, so I've mentioned those like three interesting IoT applications, and from those applications, we can see that the communication is very, very important and very, very critical in IoT. And different IoT devices have to communicate with each other through the data networks to achieve the data exchange. So for example, in the smart grocery application, a smart refrigerator needs to send the order information to the user's smartphone. And in the smart home application, a Wi-Fi access point needs to control the smart thermostat, right? So how does like two IoT devices communicate with each other? If you are very familiar with the internet protocols, TCP/IP protocol stack, which is basically a hierarchy of a software layer that defines the communication protocols between the two hosts or the two IoT devices over the internet. So the communication stack in IoT is basically applies a very similar architecture. Comprises 5 layers, the physical layer, the data link layer, network layer, transportation layer, and the application layer. So there are different kinds of protocols that are involved in each layer. So in this talk, I will just give you a very brief introduction about what those functionalities that are provided by different layers. So first, the physical layer defines the physical transmission medium, like what kind of frequency band are going to be used to achieve the wireless communications between the two IoT devices. The data link layer defines the procedure and the functions for communications between the two IoT devices in a single wireless hop distance. And the network layers provides a routing path if you want to achieve the multi-hop wireless communications. And the transportation layers that defines the procedures and the functions to ensure the reliable message delivery between the two IoT devices in a multi-hop distance. And also the application layer defines the interface to allow different software, different applications to send and receive messages to the IoT devices. So what are what is the features or what are the uniqueness of the IoT communications? Why the IoT communications is different from the other networks like our cellular network? So first of all, the IoT communication are heterogeneous, meaning that there are different types of the communication technologies that are used, such as the Wi-Fi, the Bluetooth, near-field communications, and so on. There are two major reasons that cause the heterogeneous features for the IoT communications. So first is the reason is that the different IoT devices, they have different requirements for their communications. For example, different kinds of the gas detection sensors that are deployed in the underground tunnels to detect if there's any gas leaking during the mining process. And those gas sensors are normally powered by the portable batteries. And so the communication requirement of those sensor nodes is to achieve a low energy consumption to prolong their battery lives, because to replace those batteries for those sensors is really, really challenging. So, and some of the IoT devices that are applied into the mission critical applications require low latency communications. For instance, in order to control the drones in the real time, the control station requires to have a low latency communications to send the control information to the drones in real time. So other communication requirements in IoT could be related to the distance and reliability. Some of the IoT devices requires long distance communications, but the others doesn't. Similarly, some IoT devices require to ensure the reliable data delivery. So, but other may tolerate some delivery failures. So these different kinds of requirements leads to the heterogeneous features, different kinds of the IoT protocols. So the second reason causes the heterogeneous features for the IoT communication is various network topologies. So the network topology for different IoT subsystems may differ. For example, in the smart home applications that I mentioned, different smart device in the house is connected to the Wi-Fi access point. And so the network topology in the smart home is a kind of like a star topology, where different devices do not need to have the network and the transportation layer protocols to support multi-hop communication, because their destination is always the Wi-Fi access point, which is only one hop distance. So, but in the wireless sensor networks, different sensor nodes are deployed in the area to monitor, for example, if there's any gas leaking. So in this example, each sensor would sense the environment and transmit the sensor data to the sync node or the aggregation node. But also they have to receive the data to the next hop node. So in this case, the sensor node should have the network and the transport layer protocol to support multi-hop communications. So also the network topology of our IoT subsystem could be hybrid, containing both a star and a mesh network topology. So for example, in the cellular IoT architecture here, different IoT devices, they are communicated with a nearby base station through the wireless access network. So the topology of the access network is kind of like a star topology, because the distance between the different IoT device and the base station is one wireless hop. On the other hand, different base stations are interconnected together through this cellular core network. And so the topology of the cellular core network is mesh, the mesh topology. So the topology of the overall network is a hybrid, containing both a star and the mesh network topology. So IoT communications is a key to integrate different IoT devices into a whole system and upload the data generated from the IoT devices to a data center for further analysis. So these big data are so valuable. For example, the Memphis police, they stated that they analyze crime history to predict how efficiently deploy the officers and the patrol vehicles. So basically, the crime history is going to predict when and where has a high probability to have the crimes. And so the officers and the patrol vehicles will be assigned accordingly. So as a result, the serious crime is reduced by 30%, including 36.8% reduction in crime in one target area and up to 15% reduction in violent crime. So analyzing those data, big data that is generated by the IoT devices requires advanced artificial intelligence and machine learning technologies. So for example, in the autonomous vehicles, there are many different IoT devices that have been embedded into the system, such as image sensors for the autonomous driving, ultrasonic sensors for the short-range anti-collision, and the radar sensors, which is used for the long-range objective detection, and the ECU, electronic control unit, for the on-vehicle computing platform, and the different kinds of the communication modules like LTE, 5G communication modules. They are used for the communications. So all those sensors will be utilized, or the IoT device will be utilized to determine the actions of the vehicles. Should the vehicle speed up or speed down? Should the vehicles to turn left or turn right to avoid the collision? Making these critical decisions requires advanced AI and machine learning models, such as convolutional neural networks, deep reinforcement learning models to evaluate the different actions in different scenarios. So currently, there are different number of the challenges in the context of IoT. So here I will explain some of the challenges. So first of all, designing an IoT device is non-trivial. The device often needs to be in small size to be embedded in the system. So the device has to be, maybe some device has to be of low power consumption, which is usually a key features for IoT device to survive for extended time without having the external power. Like I mentioned, the gas detection sensors, they are placed underground. It's very difficult for us to exchange the batteries. So the power consumption is a key features for those devices. Some other devices are equipped with the energy harvesters for the self-powering to survive. And the data sensed by the IoT sensors need to be of high accuracy, often leading to a compromise in the size of the power. So it's a very tricky that to design the IoT device, which can have the trade-off among the size, the power consumption, and accuracy. So how do we optimize this trade-off in designing this IoT device is really challenging. So IoT communications is also currently suffering from some challenges. For the first challenge is the connectivity issue caused by the heterogeneous features. Because of the heterogeneous features, there are there's no unique protocols in each layer. Like for example, in the there are many protocols that are developed for the application communication for the IoT communications in the physical and the data link layers. So Wi-Fi, for example, is designed for the low latency and short distance communications, and near field communications is for the low power, short distance, and low data rate communications. Bluetooth Low Energy, BLE, is also for the low power and short distance communications. But the data rate for the Bluetooth Low Energy is much higher than the near field communications. So we can see that the different protocols, they are designed for different communication requirements. So there's no unique protocol that can satisfy all the requirements. So this leads to the connectivity issues, meaning that if the two IoT devices, they probably cannot connect if they use the different communication protocols. Right. So, for example, IoT device which only support the Bluetooth connections cannot set up a connection to another IoT device which only support the Wi-Fi protocol. So the potential solution to resolve the connectivity issue is that we can design a middleware which acts as a protocol converter to convert different protocols. So for example, here the Wi-Fi access point can be implemented as this so-called the middleware to achieve the protocol conversion, right? So the second challenge in IoT communications is the interoperability issue. Because IoT devices are designed by different manufacturers, and these IoT devices may have different data modules to represent the physical descriptions of different data elements and the relationship among those different data elements. For example, as shown in this figure here, the temperature sensor could associate with many data elements which have different physical meanings. For example, the temperature sensor data element indicates a device type, and this Celsius represents the unit of the measurements, and the 24 basically implies the value of the measurements, and this measurements links to another data element, which is 13 o'clock, that indicates the timestamp of the measurement. So different IoT devices may have different physical descriptions and the relationship associated to their data elements. So a simple example is that the temperature sensor defines the temperature measurement as the temp value, right? But the Wi-Fi access points, they use this temperature measurement to describe the temperature measurement. So if the Wi-Fi access point try to acquire the temperature value, the current temperature values by sending the message to the this sensor node, the sensor node does not understand what does a temperature measurement stand for, right? So in this case, the communication cannot be understandable. So the potential solution to resolve this interoperability issue is that we can develop a universal semantic model to annotate the IoT data. It's like a dictionary that we define a universal dictionary. So all the devices, they have to follow up those rules that defined in this dictionary. So, so if you want to learn more about the semantics in IoT, you can have some additional readings by access this link here. Right. So the third challenge for the IoT communication is security and privacy. So the data generated by the IoT contains some very sensitive information. For example, the smartphones may contain the user's location information. And the Wi-Fi access point in the smart home application would maintain the user's personal preference. All those informations is private and sensitive, and so shouldn't be compromised during the communications. But the problem is IoT devices are computational limited devices. Those sensors, maybe actuators, they generally are not designed with those security in mind, meaning that it's not possible to implement some sophisticated method to secure the communications in these IoT devices. So on the other hand, in order to analyze the data that is generated by the different IoT device, these data are normally uploaded to and analyzed in a centralized facility, such as the data center or a centralized server. But those third-party data center or servers may not be trustable. So in order to solve these privacy and security issues, there are two potential solutions. So the first solution is IoT device can offload those sophisticated security solutions to the nearby trusted edge servers, like your Wi-Fi access points, which have the sufficient, relatively higher computing capacity and energy as compared to those sensors and actuators. So the trusted edge servers would assist those IoT devices to, for example, identify if there's malicious users try to access those private data. So the second solution is that if the data are sensitive, then the IoT device will not share them to the third-party data centers through the data network. Then instead, the IoT device will share the high-level knowledge or the high-level models, which do not contain some sensitive information. So this type of the privacy-preserving learning process is called federated learning. So now I'm gonna explain more about the federated learning, which is one of my current research topic. So what is federated learning? It is a distributed machine learning architecture that enables different clients in terms of the various IoT devices to collaboratively train any machine learning models over their local models. So the well-trained machine learning model can be used to provide high-level knowledge or high-level models to better service the users. So federated learning is a privacy-preserving machine learning model training process, meaning that the client does not need to share their data sets to any third-party devices. So in general, there are 4 steps in each global iterations. So first, there's a so-called federated learning server or the parameter server. It would initialize a global model and broadcast those global models to different clients. Yeah. Then the second step is once received those global models, each client would train those global models over its local data set based on, for example, if you are familiar with stochastic gradient descent or gradient descent algorithm. Then we call this model that after the local training as a local model. So after a number of the stochastic gradient descent, each client gonna derive its own local model based on its local data sets. Then the third step is all the clients, they're gonna upload their local models to the federated learning server. And finally, the federated learning server gonna aggregate all the uploaded models to generate a new global model. Then this the next global iteration gonna be triggered by go through those 4 steps again, and the global iteration continues until the global model converges. So. Next, I'm gonna provide some use cases for using the federated learning to train the different machine learning models. So first of all, the Google has been applied the federated learning to train the recurrent neural network language, which is to predict what is the next word when a user is typing a message in a Gboard or Google board. So for example, if you type "I love you" in the Gboard, the app will provide some potential words that would type afterwards. You would type afterwards. And these words are basically generated by the recurrent neural network language model. So this is the one example that a typical recurrent neural network language model, which is to predict the next words based on the previous 3 words. So here the X is the input parameter, which is essentially the existing words in your message, and the W here is a weight matrix for the input to hidden layers, and this weight decides the importance of the hidden states of the previous inputs and the importance of the current inputs. By the way, the volume is good. I see some complaints about the. I can hear some audience cannot hear the volumes clearly.
It seems okay, Shem.
Okay, good. Thanks. So let's continue. And the H is the hidden states, and in this example, for example, if you type the internet of those 3 words, then the model going to generate the probability of the next words, of the next possible words. So here the word "things" has the highest probability, and then the vehicles. So in this model, you have to decide those parameters, like, for example, those weights, they are very important. And you have to decide those what's going to be the value for those parameters in this model, right? So to determine those parameters, you have to train the next word prediction model based on the huge volume of the message or text from the users, right? Basically, once a user is typing some text in your Google applications or Gboard, those text information would be saved in a log file. So the users are not willing to share their text and the messages to the Google servers for sure. And so the Google basically is using the further learning to enable different clients training their recurrent neural network language model locally and to share the local recurrent neural network language model to the further learning server. These procedures that I have already mentioned in the previous slides, right? So the further learning has also been used for learning a diagnostic or risk assessment model for a particular disease or illness. So for example, a patient's current symptoms such as the temperature, the existence of cough and a headache, the risk assessment model can help the doctor to evaluate the probability of this the patient getting infected by, for example, the COVID-19, right? So in order to derive those high accuracy risk assessment model, which could be, for example, a neural network, we should train those models over the large volume of electronic health record here, which could be distributed among the hospitals. So the problem is that the different hospitals cannot share their patients' health records due to the privacy issues. So in this case, further learning will be utilized to enable different hospitals to train these local risk assessment models over their own health records and share those the local risk assessment models instead of the raw data to the further learning server. So there are some potential opening research topics in further learning. So first problem is that in further learning is that the client selection. How to select suitable clients to train the machine learning models. So due to the heterogeneity of the clients in terms of the IoT device, different clients have their different latency to train and upload their local models. So here the heterogeneity means that IoT devices have different computing and communication capabilities. So for example, let's say that there are 3 clients here, client 1, 2, and 3. Client, they try to participate in the federal learning process to train the local models and upload the local models to the federal learning server. So the client 1 and 2 have the relatively high computing and communication capacities, and so they can train and upload their local models to the federal learning server in a short latency. But the client 3, probably it has a low computing and communication capacities, so it requires a much longer time to train and upload its local model. And so we call this client 3 in this example as a struggler, which may significantly increase the training time. This is because in each global iteration, the federal learning server has to wait for a long time until this struggler, which is client 3, to upload its local model. Right? So there are two types of the solution to solve this struggler problem in federal learning, which basically categorize federal learning into two types. So first, the first type of the federal learning is called synchronized federal learning, which is to set up deadline for all the clients. And so the clients who upload their local models after the deadline, then those models will be discarded. So it is necessary to select the clients that can finish their local model training and uploading before the deadline. So the second type of the federal learning is called asynchronized federal learning. So the server would immediately aggregate the models once it receives a number of the local model from the clients. So when to initialize the model aggregation really doesn't depend on the deadline anymore. So for example, let's say that the federal learning would immediately aggregate the models once it receives the two local models. Then in this case, the federal learning server would generate a new local model once it receives the local model from client 1 and client 2. So it does not need to wait client 3, right? They're gonna first generate the new global model and then broadcast the new global model to both client 1 and client 3. So the second problems in federal learning is the model aggregation, meaning that how does the federal learning server aggregate those received local models to generate a global model? So in the traditional federal learning, like the federal average, which is proposed by Google, it just take the average of all the parameters in all the received models. So here, omega I represents the parameters of the local model from client I, from IoT device I. And this cardinal node DI is the total number of the training data samples at the client I. And this cardinal node D is a number of the training data samples for all the participated clients. So this method works fine when the data samples are independent and identically disputed among the IoT devices. But the accuracy of the model is reduced in the non-IID scenario. So there are two ways to handle the model aggregations. So in synchronized federal learning, the federal prox has been proposed to add a so-called the prox term to the local subs problem to efficiently limit the impact of the variable local updates caused by the non-IID distribution. So if you want to know the details, I would recommend you to check this this paper. And the other solution is called asynchronized federated optimization, which basically is based on the weighted sum of all the global model and the received local models of a client. So here the weight basically indicates it's a function of the local model staleness. And again, if you want to learn the details, please read the papers that I listed here. So due to the time limitation, I will not explore more on those two solutions. All right. And finally, I would like to just to give you some brief introduction about the IEEE Academies on Internet of Things. This has a variety of the courses that related to Internet of Things, and now it is available on the IEEE Learning Network. And right now there are two, I would say, themes. One is IoT communication standards, where you can learn a lot of different kinds of the standards what is their what are the pros and cons for different protocols, right? And the other themes is IoT computing platform, which basically is give you some very brief, very detailed concept and the solutions to explain how the different computing platforms that are associated with IoT. Oh, thank you. That's all my talk. Thank you for being here. And if you have any questions, please feel free to ask.
Thank you very much, Jiang. It's a really wonderful presentation, very, very informative. And we've got a good few interesting questions. I'll fire them away immediately. The very first question is from Angelique Parashis. She basically says that we're hearing about a lot of technologies such as IoT, AI, mixed reality, but there's also smart cities. Can you give us an example of an effectively running smart city that encompasses IoT for its sustainability?
Thank you. So it's a very good question. So the smart city definitely is one of the IoT applications involving a lot of technologies. Like you said, the AIs, the VRs, the IoT communications, and the different kinds of the machine learning models. So definitely IoT plays a very important role here because in order to connect all different kinds of the smart devices, you should have the IoT communications to support that interoperability connectivities, right? So, and also on top of the IoTs, you should have the different kinds of the machine learning models. One typical example is that if you want to have some traffic management, you have to have the different of the interconnected cameras of the flying drones that are detecting the real-time traffic. And all those informations are captured by the CCTVs, right? And may be aggregated to an edge service or the data center. And the edge service and data centers, they can apply different kinds of machine learning models to provide what are going to be the high-level knowledge. For example, what are going to be the traffic right now? What will be the traffic in the future, maybe in a few hours, right? And those machine learning models going to be trained, for example, based on the federal learning if there's some privacy issues. Thank you.
Great. Thank you, Xian. The next question is from Yuan Chu Luo. It's on a topic that's actually one of my favorite. Can you share your comments on the Internet of Nano Things, especially the different points in terms of technical challenges?
Oh, this is a very good question. So I don't know if I have the right answers, probably, but this is just based on my understanding. So for the Internet of Nano Things, I would say that the power consumption is much more important than our traditional Internet of Things because it's and also there's some since it's the power consumption is a key challenge for the Internet of Nano Things. So the different kinds of the communication protocols, they are tailored for the low power consumption the features for that. And I think that's basically my understanding. The most important thing is that between the Internet of Things and the Internet of Nano Things is that in Internet of Nano Things, the power consumption is the key challenge. But in the Internet of Things, there are other challenges. Some IoT devices, they really want to achieve them high data rate communication protocols.
Yeah. Great. The next question is from Hezekiah Samwini. In the case of processing IoT data at the network edge, is it feasible to run middleware on the edge devices, such as edge network devices that do not have sufficient resources? And he's asking this in the context of edge or fog computing.
Thank you. I think also a very good question. Yes, of course. like I said, different edge devices, they should have very limited computing capacities. So the needs are different. IoT devices need to, or the edge service need to collaboratively analyze or train the data. So in this case, we should have some to achieve some like a distributed or collaborative machine learning models or machine learning architecture, like I mentioned in the federal learning. That really doesn't need a centralized service to analyze the data, right? So the combination between the edge device and the federal learning can achieve this kind of collaborative machine learning, which does not allow like a data center which has sufficient computing resources to consume those data.
Thank you, Xiang. The next question is from Jonathan Beverly. With increased adoption of LoRaWAN and 5G connectivity, does this mitigate some of the security concerns one would have in leveraging Wi-Fi?
So thank you for this question. So I'm not the security expertise, so probably I may not give you the answers that you want. But based on my understanding, the security will not be mitigated. As far as I know, there are different kinds of security solutions that has been proposed, has been used in the 5G network. Right? But again, I'm not the expertise on that. But I hope that my answers, gonna give you some insights. Thank you.
Sure. The next question is from Ismail. How do you make a balance between training set and test set in federated learning?
Yes, that's a very good question. So the federated learning itself is kind of like a training process that does not test the accuracy of the model. Like I mentioned, in federated learning, there are different types of different 4 steps. So the global iteration gonna be terminated. There are 2 criteria. One criteria is that if the global model is converged, so we just stop the training. So the other criteria is the accuracy of the model. If the accuracy achieves our desired threshold, then the training is stopped. So in the federated learning itself, we really doesn't test this the accuracy of the model. But some of the federated learning method, they just propose that when we train upload the local models, we first test these models based on the local data set. And if this model achieves a high local data set, then it's gonna be associated with a high weight when we aggregate the local models. So there's not a very clear definition about which portion or which percentage of the data set should be used for the training, which percentage of the data set should be used for the test. Right? But again, the federated learning is focused on the training part. It really doesn't care about the testing. But the testing result is used to calculate the weights of the local models. Thanks.
Okay. So we'll have one last question, Xiang, and the last question is again from Angelique Parashis. Every few years we hear about new technologies. First it was smart grid, then IoT, then smart cities, now AI, AR, VR. What do you think is the next technology that we may be seeing emerge as these technologies all progress?
What is the next technology? That's a very good question. So I cannot predict what is the next technologies that are going to be emerged. But But I would say that the Internet of Things are going to be developing for several years. And what I'm saying, the IoT is developing means that the IoT going to be involved with, going to be associated with different kinds of the technologies, like I mentioned, the AR, VR, the machine learning, the autonomous vehicles. All those technologies going to be combined. Maybe in the future, the IoT going to combine with quantum computing and quantum communications. Who knows? But I really cannot predict what are going to be the next new technologies. Thanks.
Great. Thank you very much, Xiang-san. Look, the time is up now. We have many other questions, but unfortunately, we just don't have enough time. Thank you very much once again for your presentations. Really, really great presentation, great session. This is a really, really great initiative, the IEEE Academy Internet of Things. I'd encourage people to go and look at the website to learn more about it. There's plenty of information for training, especially for the younger generation as well, to get into Internet of Things amongst other topics. So thank you very much, everyone, for attending today, and we look forward to the next webinar series. Thank you, Xiang.
Thank you.
Thank you, everyone.
Thank you.
Take care.
Thank you.
Thank you both, Dr. Xiang. And just a reminder that an on-demand link will be sent for today's event approximately 2 hours after the session ends. And please be sure to complete our feedback survey via the Teal survey tool at the bottom of your screen. Thank you and have a great day.
Great. Thank you, Joanna. Thanks, everyone.
Bye.
Take care.
Thanks. Bye. Take care.